The mean value theorem for integrals. We've talked about the mean value theorem for derivatives before, right? But this is for integrals. If f is continuous on some closed interval a to b, that has to be true, or we can't use mean value theorem for intervals, right? Keep that in mind just in case we give you some function that's not continuous, right? Then the mean value theorem would not work. We wouldn't even try it, okay? Then there exists some number c, which we're not going to tell you how to get just yet, on the closed interval a to b, such that the antiderivative from a to b, f of c, f of x, dx equals f of c times b minus a. So what does this look like graphically? Let's see here. Let's draw a little graph. And let's add some fun stuff to it, maybe like that. And we know the antiderivative from a to b of f of x dx is area under the curve from a to b, right? And when we say area under the curve, it's understood that's the area under the curve between the x-axis and the curve, right? All right, so let's say the interval is like maybe a is 0. Let's put b out here at the end. Okay, now let's think about this for a minute. What is f of c? What is that going to give us? C is in between the two, but it's a what? It's a y value that corresponds to an x value in between a and b, right? Okay, what is b minus a? That's change in x, right? So this is delta x, which is the width of some interval, right? That's a width of some interval. And what was this again? Which is what? Yeah, like it's a y value, but you know, maybe use a different word. What else do we call y values? Heights, right? Heights. That's a height. F of c is a height. This is the height times width, right? What does that create then? Area of what? Not necessarily. It's area of what? What figure? Rectangle, yeah. Well, not necessarily a square because we don't know if these are the same. Okay. So they're saying this area of the curve can be expressed as some height times the width. So what that means is, if I change colors here, there's some c value in between a and b such that f of c is the height of a rectangle that gives us the same area as the area under the curve, between the curve and the x-axis. Okay, and that would be considered the mean value. Average value, average amount, that would be that f of c value. Here's c, obviously. And we could put, for fun, let's put f of a here, and then f of b up here. There we go. C is an x value that corresponds to f of c, which is the height such that this rectangle has the same area as the curve. There exists a c in the closed interval a to b. Just in between. Yeah, it just so happens that for my drawing, it's pretty much in the middle, right? But to have it be about the same amount here as you do here, right? So if we kind of like put this here, it covers it up. Now, what would happen if we had a couple like curves and stuff like that, and I went to like B over here, and this is A? Well, maybe it's up here. I don't know. And it could cross the curve a couple times, right? That height could be on the curve a couple times. And again, I don't know if this is exactly the same as the right spot. I'm just kind of visually demonstrating how it could look. Okay, and so this right here, this is the average height. The average height of the function. Now, this mean value theorem is not typically on the AP test too much, but a variation of this is. Okay, that would be the average value. If this is the average value of a function, well, isn't this equal to f of c then? Right? That c value that was between a and b, that's that height that corresponds, which would be the average height of the function, or average value, average amount. This is always on the AP test. Okay, f of c is that average value. Which is the same thing as the average amount. Now look at this, guys. This is 1 over b minus a. So this would be the area under the curve, and we're essentially dividing it by the width of that interval. That gives you an amount. You take your area and divide by your width, okay? Now look at this. Go back to the mean value. What if we divide both sides by b minus a? That'd be 1 over b minus a over here, right? And f of c, okay? So the average value function is the same thing basically as a mean value. Okay, now how will this look on the AP test? They'll say find the amount given, or the average amount, my bad. I'm just going to erase that. Find the average amount given an amount. Find the average rate given the rate. And again, if we look at it graphically, that height, that f of c, that is the average then that we came up with, right? This is that average. I think I have a nifty little drawing. Yep, I do. Down here, as you can see, you know, if we have some sinusoidal graph, that average height pretty much cuts that graph in half, right? Questions so far? Well, let's actually do a practice problem then. Here's how a problem could look. Find the average value of f of x. Average value of f of x equals 3x squared minus 2x on the interval 1 to 4. Okay, now we're going to be using our calculator quite a bit, right? We'll probably do this one by hand, but we'll check with the calculator. But before we enter anything in our calculators, you always have to write out your setup. You get credit for setup on the AP test and on my quizzes and tests too, right? So how would this look? Well, I'm going to write it as basic at the beginning. But after we write it out once or twice, we know what numbers to fill in, and we won't waste our time doing it this way, right? So that's your average value, right? Okay, 1 over b minus a. Well, we know what a is. We know what b is. So 1 over 4 minus 1. Antiderivative, 1 to 4. F of x, that's 3x squared minus 2x. Parentheses needed. And then dx. All right, now what? Let's see here. Well, think about this. This is the area under the curve. You divide by the width, and you get a height of the rectangle. Okay, that would be your average value. Let's keep going with this. 1 over 3. Okay, let's see here. Maybe what? X cubed divided by 3. Well, that's convenient. Minus x squared divided by 2. That's convenient. I like this problem. Why no plus c? Yeah, this is a definite integral we're working with, right? We're evaluating. So 1 to 4. Okay, 1/3. Would that be 4 cubed minus 4 squared? Minus, begin another parentheses. 1 cubed minus 1 squared. So 1/3 of. Ooh. I always double my 16s. So I get 64 minus 16 minus 1 plus 1. Minus 1 plus 1 cancel. Add to 0. And what would that be? 48? What's a third of 48? 16. That's my reasons. How do you find the c value now? How do you find the x value, which is c, right? We know c is x. How do you find c, though? For what? For f of x, yeah. This is a height, right? So you want to figure out when is the height 16. So you go 16 equals 3x squared minus 2x, right? And then we can either algebraically solve for x. We can use your calculator, solve for x. Y1 is 16, y2 is this garbage. See where they cross, then that's the x value, right? Okay, you can subtract 16 over, set equal to 0, find the roots then. We know how to solve for x, okay? And so we could find that c value. Anybody find it yet? And again, we're only looking for the interval 1 to 4, so if it occurs more than once, I only want those ones. 2.66666. Yep. All right, 6 is approximately 2.66. I'm a truncator, guys. You guys know that, right? Except for this one, 7. Now, here's something new. Actually, it's not. That looks familiar, doesn't it? That's just the first fundamental theorem of calculus, right? Well, we use that first fundamental theorem of calculus to find other things, and one of them is net change. Okay, the definite integral of the rate of change of some quantity, f prime, capital F prime this time, gives the total change or net change in that quantity on the interval a to b. And then we know capital F is the antiderivative of capital F prime. So if this is the rate, what would f of b stand for? So if you integrate a rate, what do you get? An amount. That's why I usually say it, right? Integrate a rate, you get an amount, right? Integrate a rate, you get an amount. So if you integrate this rate, what do you get? An amount, right? Specifically, amount when? At the beginning or end. Is b the beginning or end? End. So this is the amount at the end. And what would this be then? Amount at the beginning. Okay. And you guys know this, like the amount at the end minus the amount at the beginning is your change, isn't it? That's why this is called net change also. This whole thing we consider the net change theorem. Okay. This is how much you change. Okay, let's kind of do an example problem. We'll stick with bananas. Bananas. Banana. How do they say that? on the table. Bananas are added to a table at a rate of B prime. Are on table, rate B prime. Who needs filler words? This is math. We know what's going on. Bananas are being added onto the table at a rate of B prime. Okay. There were 47 bananas at t equal 3. How many bananas? At t equal 7. Okay, they might give us some functions. Bananas were being added to a table at a rate of da 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 da. There were 47 bananas at 3 hours into the day, or 3 hours after the store opened, or something like that. How many bananas would be on the table at t equals 7? Later on, we'll add in subtracting bananas and stuff like that too. Well, how do we figure out how many bananas there were at t equals 7? Well, use antiderivative. So a to b. What is a though? A is 3. B would be 7. B prime. Oh, let's call it x for fun. Dx. Actually, sideways t's, right? My bad. I used t already. What would this equal? Well, antiderivative of lowercase b prime would be lowercase b evaluated at 7 minus lowercase b evaluated at 3. Okay. Now, we would use our calculator to figure this out. They'd give us a function or something, right? What is b of 7? What we're trying to find, right? The amount at 7. What's b of 3? 47, okay? So what happens if we solve for b of 7, the amount at 7? You'd add 47 to the side over here, right? So it means you'd start with 47 and you add on the change between 3 and 7, which could be negative, could be positive. And that's just how much you have left after 7 minutes or something like that. All right, well, let's start a problem. Then I'm going to add something to it. A chemical flows into a storage tank at a rate of 180 plus 3 t liters per minute. We know it's a rate. Why? They told us, and we know the units are liters per minute. Just by knowing that, we know this is a rate at which that chemical is flowing. Okay, this is the derivative. This could be dr dt if you want it to be. Where 0 less than equal to t less than equal to 60. Ooh, is it hours, minutes, seconds? What is it? It is minutes, okay? We caught that now. We got to be more observant and ready to take care of this. Just in case they ask us about hours down here. They might do that sometimes. Or Mr. Bonley might have it on a quiz like that sometime. Okay? Find the amount of chemical that flows in the tank during the first 20 minutes. And then they go and put in 20 here. Okay? Well, let's figure out how much chemical flows into that tank. To do that, we have to integrate the rate to find the amount. So integrate the rate. And what are our bounds on our integrate? 0.60? Are you sure? 20, because they said 20 minutes, right? And then we have, what, 180 plus 3t. Whoops. T. And then dt, right? If you would, just use your calculator really quick. We could do this by hand. That's pretty easy, right? But use your calculator real quick. Now, are you guys using Math 9 or are you using your graph? Math 9 is pretty easy. It has that math type on there. Go ahead, use it. 4,200? What's the units? What? Okay, if we're integrating liters per minute, remember when you integrate, you multiply by time. So you multiply by time, minutes cancel, you get liters. That makes sense? And the reason why, because we'd have the dt, differential with respect to time. Loosely, we can think about it like that. Okay? All right. So that's easy. We've done that before. Okay? Well, suppose there are 430 liters of chemical in the tank at t equals 2 minutes. Okay. How much chemical in the tank at t equal, now I have to keep my number, I'm going to pick under 60, 58 is a good round number. I suppose their initial quantity was 430, and we want to figure out at 2, I should say initial quantity at 2, how much is in there at 58. Well, how do we set that up? Well, this is where that net change thing comes into place. When in doubt on these problems, you're given a whole bunch of stuff, right? When in doubt, use the first fundamental theorem of calculus. Always, always, always. It's fundamental to calculus, okay? Especially if they're talking rates and amounts. What's the connection between the two? Antiderivative, okay? Well, let's see here. The antiderivative of, let's see, where do we start at? 2 and at 58. And then this is how much is flowing in, the rate at which chemical is flowing in. This would be the amount that is added between 2 and 58 minutes, correct? Equals, now we'll call this function, we'll call this f prime. So then if we integrate f prime, it would be f of 58 minus f of, and before when we did this definite integration, we didn't consider these like the ending amount and initial amount, right? But in this word problem, it is. Okay. So what is f of 58? Oh, it's what you're trying to find, right? What is f of 2? The amount in the tank at 2, right? 430. Okay. So we use our calculator to figure out this amount. That's the change. And when somebody has it, give it to me. And then f of 58 is the amount at 58 minutes minus the initial amount at 2, 430. And look at this, you take your initial amount, add the change, you get your final amount. So add 430, and we get what? F of 58 equals 155, ooh, cool, 15550. And then liters, right? So we would make this a little more specific. We'd say there are 15,550 liters of chemical in the tank at t equal 58 minutes. Okay, but do you see how we're using the first fundamental theorem of calculus to figure out like an amount at the beginning or an end of a time period? Okay, so that's called the net change. All right, questions on this? Let's go on to the next thing. Another way to illustrate this net change theorem is to examine the velocity of a particle with the position. Because what's the antiderivative of velocity? Position. And you guys attacked physics in this kind of matter. You do like final position minus initial position, right? And this is change in position, right? Antiderivative of your velocity is change in position, right? That's just final minus initial. Well, if you don't know these, you got to use this, but we can help find another one knowing a different one. Okay, now this would be your displacement also. Final position minus initial position. Okay, let's say we go from Bismarck to Minneapolis back to Fargo on a trip. What's our displacement? About 200 miles, right? Is that our total distance traveled though? No, that's our displacement. That's your final minus initial, right? Okay. And that'd be a negative 200 because that'd be like a vectorish kind of idea, right? Going backwards. Actually, well, I'm looking at it this way, negative, so it'd be actually positive going that way. There we go. That makes sense? Because you're going positive to Minneapolis and then negative back to Fargo. So that 200 difference, that'd be positive direction still, so that'd be positive 200. Okay. All right. What if I asked us about total distance traveled? How would we find this? How would you find total distance traveled? If this is your displacement, which means distance between your final and initial position, what would be total distance traveled? What do you mean? Sure. How about using an integral? What would you do? Think about this. Okay, let's use that. Let's go on the fly right now. Let's use that idea of going to Minnesota. If v of t is our velocity, from 0 till we get to Minnesota, we'll say we get to Minnesota at C. Start at time A. What's our velocity if we go to Minnesota right now? Minneapolis. Would it be positive or negative? If we consider that way, if we're facing that way, we're going that way, right? That'd be positive, right? Okay, so that means our velocity graph would be up here. That means we're traveling right, correct? And the area under the curve would be distance traveled, right? Okay, because that'd be rate times time, which is distance. Okay. Now when we come back from Minneapolis to Fargo, say we get to Fargo at B. What would our velocity be? Negative. So the plot of our velocity graph should be negative, right? Now, if I took this positive and added it to this negative, we should get about 200, right? Okay, this would be distance traveled. The area under here would be distance traveled for each one, right? That'd be positive distance, negative distance. That'd be the negative. Okay, you guys got it. Now, how will we set up an antiderivative, though, to get us total distance traveled? Of what? Yep. A to B, absolute value, V of t, dt. And a lot of times, all we have to do is write this, use your calculator, calculate it, because the calculator does a very good job of finding this, right? You know how to find absolute value in the calculator. Hit enter, and we're done, okay? Now, remember what the absolute value does is takes all the heights, makes them positive, takes all these heights, makes them positive, right? So therefore, you'd have a positive and a positive, correct? Okay, so keep that in mind. Questions on that? If we weren't able to use your calculator, we might have to break this up, right? Find where the absolute velocity is 0 and split it up. All right. Cool. Let's go on to the next thing. And we're going to spend a lot of time next week practicing these problems and taking about 5 more quizzes. Not 5 more quizzes, but you know what I mean. A particle is moving along a line, vertically or horizontally, doesn't really matter, so its velocity v of t equals a nice, neat polynomial. Feet per second is our unit of our velocity, and it's time t, and t is in seconds, and s would be in feet, right? What is the displacement of the particle on the interval 1 to 5? Well, we know displacement is just final position minus initial position. How would you do that? You integrate 1 to 5, v of t dt, correct? Which would be 1 to 5. Now, good thing we have calculators. Use your calculator. I don't want to evaluate at a 4th power right now. Let's use your calculator for that one today. And what they might ask us, they might not ask us what's the displacement. They might ask, is the ending position to the right or to the left of your initial position? They might ask us that too. Okay, what do you guys get for an answer on this? Okay, and we know, let me say this, we know that this would be s of 5 minus s of 1, right? And again, 7 units. All right, part B, what's the total distance traveled? Now, should that number be more or less than 10.667? Hopefully more. Could be exactly, should not be less though, right? I'm hoping so. So we'd go antiderivative, and we're writing this out before we type in our calculator, right? Because you would get a point for writing this out. And then just go equals, and boom, you get it. What are we getting? 11.833. All right, well, let's take a look at the graph. Because I want us to analyze real quick how we would set this up if we needed to split it up. That means we got to find out when velocity is 0, right? Well, let's pretend we can use our graph. And I already have it typed in. And look what I did. I adjusted my window so it's 1 to 5, right? We can find that root pretty quickly. Calculate. Let's go to 0. And again, let's see here, move my cursor to the left, hit enter, move it to the right, hit enter, guess, whatever. Okay, it's exactly at 4, right? Okay, now look over there by 5. It's kind of weird. Like, is it cross again before 5 or not? So what I do sometimes, I'll hit trace, and I'll just kind of sneak the cursor over there, and notice how your heights are still negative. Does that cursor jump positive before 5? Ooh, it's exactly 0, right? And we could have done that by just extending our window a little bit and calculating the 0 too, right? So sometimes it's easier doing this. So we would have to set up our antiderivative. Let's see if I can write this thing again. Nope. It's a good thing I came prepared with 2 of them open. So we have to have our antiderivative would be what? Antiderivative 1 to 4. Now, guys, look at velocity. Do I put the negative on this part of the velocity or the positive? Which one? Is this one positive or negative? This one's positive, right? Because velocity is positive right here. So that's just going to be v of t dt, right? Plus antiderivative 4 to 5 of negative v of t dt to get this area under the curve to be on top, right, in the quadrant 1. All right, so that's how we have to have it set up. Now, we got to keep that in mind. Maybe they might ask us a question of how would I set this antiderivative up to find the total distance traveled or to find the displacement. We got to know how to do both. All right? Questions on this so far? I think after we practice this, we'll solidify our skills, but you got to be able to know some of the theory or the philosophy or the reasons why we set it up the way we do, so you're not just stuck in doing things one way. You, like, given any type of problem, you can set them up. Okay? Get you guys ready for anything.